Welcome back to lecture 27. So today is the second last lecture of this week and we will continue on our discussion on pseudomorphic HEMT, but more importantly we are talking from the point of view of power amplifier. So where we discussed things like air bridge and multi-cell. Okay, so we will continue on that and we will move to low noise application and then indium phosphide HEMT. So over to the whiteboard here. So this is the last slide that I had shown you in lecture 26. As you can see that combining different power cell is very important. Each cell consists of many multi-finger devices. This is one device, this is one device. So okay, so you have many multi-finger devices that are being brought together to make this huge periphery device. Okay, so power cell combination is important to form very high power devices, microwave devices, composite high power microwave devices, and you have to account for gain degradation. I told you as the signal propagates it dephases, so that gain degrades a lot because of dephasing. So the design has to take account for that, how you bring in the signal with wire bonds or via holes, that has to be really carefully designed. Most of these designs are not only device design but also you have to do design at the amplifier level with ADS simulation software, for instance example. If when you have large periphery devices you have very low input impedance, you have to leave it that. What does impedance mean? We will come to that towards the end of the course in the microwave engineering. You always need to match the impedance, for instance. There always have to be appropriate gate and drain bond pads for wire bonding, for instance, for defining the inductances, and the end user could be free to combine, as I keep telling. They can combine at the package level probably, or it could be provided in a bare die form. So as I told you, when you do not need to do an on wafer characterization, on wafer characterization is in the developmental stage. Once you develop the device, you understand each cell working differently. What is the power level, gain, efficiency of each cell, each device, then you do an on wafer. But once you have matured the process, you combine and you actually do not have the CPW GSG configuration. What you have is common gate and bus bar, from where you actually wire bond, for instance, or depending on the cell, and you have to bring in stability design, by the way, stability design, because such big devices with large power will tend to oscillate. They will not be stable. The gain will, the output will basically couple to the input, it gets amplified and go out again, come back. So it's like a feedback, a positive feedback leads to instability. So you need to intentionally put a resistance in the gate part so that you reduce the gain, you sacrifice the gain so that you get better stability. So you do not let the device oscillate. Okay. So the layout is very important. Okay, and you have to understand that on wafer as well as a package device are also very different, in that way. From the point of view of a package power device, because you have to eventually package them nonetheless. Okay, when you want to sell it, or there could be packaging entities, but in general from the package point of view, some of the impedance matching could happen inside the package. It is called internally matched package or internally matched FET. So what does it mean? It means that any device when it looks at the output, you will have some kind of impedance. Impedance is a complex you can say resistance, it is in the form of A plus JB. If you have done your undergrad engineering, you will know what impedance is. It considers the magnitude and phase essentially, and it is a complex number because you have capacitances, inductances, so it is a complex version of the resistance in a way. So when you have an impedance on the output of the device, you want to deliver power to a load, a ZL. A load will have its own impedance. It could be in the form of X plus JY. So your A plus JB of the output impedance has to be transformed to X plus JY, which means you have to match in a conjugate way. There could be matching for optimal power, matching for optimal gain, etc. But in general you need to match them, which means you need to transform one form to another form. It is called impedance matching. Only then your reflection will be minimum. Okay, what semi qualitatively speaking, what it means is that your RF signal that propagates, and there is a load here ZL, it will hit the load and it will bounce back and return, correct. So that reflection, you want that reflection to be minimal, as close to possible 0. So that whatever you are sending should transmit, it should not reflect and come back to the device again. So the reflection coefficient gamma stands for the reflection coefficient, should be, you should try to minimize the reflection coefficient. Okay, you do not want a reflection coefficient, so you need to match the impedances. So this impedance matching is typically done with some kind of an RC circuit. You need a capacitor, you need resistor either in series or parallel, and this need not be as the frequency increases you cannot use a lumped element. So, you can buy these resistors from the market, from the street shop. You can buy resistors, you can buy capacitors, you can put them on a board or a PCB that works for lower frequency, maybe a couple of gigahertz, but when you go to higher frequencies, X band, K band, Q band, etc., those kind of approaches are very difficult because your wavelength of the signal is actually very low, lambda, you are approaching millimeter wave. So, at that kind of frequencies you have to use a transmission line, T line. Transmission line basically is a metallic line on the board. You have a PCB or a Rogers substrate or some kind of a board, on that you have this metallic lines that you can print. The width of the line, the dimension, the angle, the taper, etc., they will all matter. That line, the metallic line, and we will see pictures of that, the metallic line will have its own impedance, characteristic impedance. You can use the metallic line with open short structure, series parallel structure, which will behave like a capacitor or a resistor, and so using that combination you can make a matching network using transmission line to represent capacitors and inductors at higher frequencies. At lower frequencies you can use a lumped capacitor or an inductor or other things that you can buy from the street market. Okay. So, that matching circuit is needed to actually make a power amplifier, so that your reflection is minimum, you transfer the maximum power to the load, or you have the maximum efficiency or gain. So, that matching network could be inside the package, which means you have a discrete die and this is your package. Suppose inside the package you attach the die, the die means the discrete transistor, multi-cell could be, and then you have the matching network implemented within the package. So, it is called internally matched power amplifier or internally matched device. You can say it is an internally matched transistor. Okay. And by including the matching circuitry at this level, you are essentially making the package insensitive. Like you can give the package and say I have a package which is internally matched. So, the customer will be very happy, they do not have to design the matching network. Now, the question here is, how do I know what load this device is going to be used? If I do not know what load the device is going to be used, how can I design the matching network? Because the matching network has to match the output impedance to the load. So, there is a very common, very useful thing, and which is 50 ohm impedance. 50 ohm is like the universally accepted impedance, or you can say the resistance, that all microwave engineers and circuit designers talk about. So, when you say internally matched device, typically, okay, you have a device where the output impedance is transformed into a 50 ohm. That means outside the device, outside the package, outside the package, looking in the package, you will see there is a 50 ohm impedance termination. So, when you give this to a customer, could be a civilian, military customer, you can say that I have a package device which is internally matched 50 ohm. They will be very happy, they will take it, and then they know it is 50 ohm, they will have the system also at 50 ohm. They may have a load eventually at different complex impedance, but the idea is that 50 ohm is the universal impedance. So, 50 ohm is very easy. So, you have 50 ohm, you can quickly match them. Okay. So, 50 ohm is like the holy grail, it is like the universally accepted impedance that you want to match. So, 50 ohm terminated in impedance that you have to do. The impedance circuit has to be designed like that. What I mean is that suppose your output impedance is suppose 20 minus 30 j ohm, you need to add a resistor capacitor network that will give you 30 plus 30 j. If you add them together, 30 plus 30 j, 20 minus 30 j, this and this will cancel out, you will get 50 ohm. So, you have to implement 30 plus 30 j in a impedance matching network inside the package, that is all it means. Okay. Now, that was all about power amplifier, very good, but pseudomorphic HEMTs are also very attractive and useful for low noise application. Now, low noise applications do not need high power densities, they do not need such large periphery multi-finger devices for handling or delivering high power, but they have some other requirement. You do not, if you recall, for high power devices we had two dopings, both on the front of on the top of the channel, on the bottom of the channel, so that both of them will donate electrons for a high 2D electron gas, because only a high 2D electron gas will enable you to carry high current. In a low noise amplifier, that is not strictly necessary. So, what people do is that they just have one delta doping layer on the top of the channel. This is a spacer, you can see that it will donate electrons here, and you will get some 2D electron gas concentration, not probably as high as in the power amplifier case, but it is pretty good enough. Your drain current requirement is low, you do not need exorbitantly large drain currents to flow. Okay. However, you need, as I keep telling in the MESFET lectures also, you need very high GM which means you need to have really high transconductance, you need to have very good channel control, recess gate for instance, thinner channel, you need to have really high FT, or you can say both of these can be met by a really small gate length, correct, and your gate resistance should be also as small as possible. These are some of the requirements for a low noise amplifier. And if you, and I keep telling you, so pseudomorphic HEMT, if you forgot what pseudomorphic HEMT is, it is using a gallium arsenide buffer. You strain the layer of say 15 nanometer, 15% or 20% indium gallium arsenide, which is lattice mismatched to gallium arsenide. However, you do not let it relax, you grow it within a critical thickness such that the lattice mismatch strain is accommodated in this layer, in this channel layer. So that is why it is called strained, or it is a pseudomorphic layer, pseudomorphic HEMT. This substrate, this platform of gallium arsenide is cheap, and you can get large wafers like 4 to 6 inch wafers. So scalability is good. Okay, the process is very mature on gallium arsenide platform. So that is why for wafer size, cost, economy of scale, process maturity, etc., pseudomorphic HEMTs are really attractive for low noise application, also in terms, in addition to power amplifier. Okay, so how do performances of low noise application, and I told you that in low noise application the gain matters a lot, okay, in dB, and what matters a lot is noise figure, or you can say minimum noise figure. So noise figure is the, I keep telling you, it is the 10 times log of signal to noise ratio at the input divided by signal to noise ratio at the output. Minimum noise figure is the noise figure that we can get when everything is optimally matched for the lowest noise possible. And in case of noise amplifiers, low noise amplifiers, the input is more important because noise is usually referred to the input side. So input matching is very critical, okay, input matching is very critical. So maybe I will remove this annotation so you can see the table that I am putting you here. Yeah, this book is from this book, RF and Microwave Semiconductor Device Handbook. You can see these are the frequencies, the frequency is increasing, at that frequency you are measuring noise. As of increasing frequency your gate length reduces, obvious. You have noise figure that starts degrading, of course higher the frequency worse is the noise figure. We talked about this in your couple of classes back where we talked about the LGAS gas baseline HEMT, or even MESFET for that matter. Your gain reduces with higher frequency, that is obvious, gain reduces at higher frequency, and because gain reduces with higher frequency your noise figure also reduces at higher frequency. And you can see these are package device, reduction by LG, reduction by RG, etc., etc., different reports by different groups in industry or academia. But the key point here is that you can get to noise as low as 0.6 dB noise figure. That is a really impressive noise figure for a frequency of 12 gigahertz, okay, and you are using a gate length of 250 nanometer, okay. Of course if you increase the frequency you sacrifice, but still you get less than 1 dB of noise figure even at 18 gigahertz. These are remarkable numbers, as we will see, these are remarkable numbers. Even at 94 gigahertz, which is W band, okay, the noise figure can be as low as around 2 dB, and that is really impressive gain, excuse me, 6 dB. So pseudomorphic HEMTs are really attractive for low noise applications also. Finally, pseudomorphic HEMTs are also very useful for wireless and smartphone mobile power amplifier market. Power amplifier, as I keep telling you, guzzles up or uses up the most largest fraction of the battery's energy, okay, and so power amplifier is mandatorily made in a 3-fab compound semiconductor platform in all leading smartphones today in the world, okay, all smartphones in the world the power amplifier has to be a compound semiconductor based device, could be HBT, could be HEMT, but it is a compound semiconductor. Silicon devices, it's very difficult to get that kind of specs for a battery operated small handheld cell phone, okay. So you can see here requirements for a smartphone. If your device is going inside a smartphone, it has to have very stringent set of requirements. First of all, the smartphone will give you a very limited amount of battery output voltage. So that output voltage typically is the drain bias. You can see this. What do you see? You see 1 volt, 1.3 volt, 3.5, blah 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 blah, 3.5, maximum 4.7, maybe 5 volt, but typically 3 volt, 3 to 4 volt, 3.3, 3.5, 3.7, 2.5, etc. That is your drain voltage at which your power amplifier device needs to be biased, okay, or a low noise amplifier needs to be biased, which means your device should be able to give output power in a drain bias as low as 2 or 3 volt. If you recall the power amplifiers that we discussed in general, they have a fairly large bias, you see the bias here, 7 volt, 8 volt, 9 volt, 9 volt, 5.5 volt, but that is not yours inside the cell phone. Once you are inside the cell phone, your power, your output voltage is low, you will have the battery limitation, and so you need to have this kind of voltages. And for that kind of voltages, what kind of power you need? Typically 1 watt, you can say close to 1 watt is the power that you need. So 30 dBm is 1 watt, okay, and 20 dBm is 100 milliwatt or 0.1 watt. So this is close to 0.1 watt, this is slightly more than 0.1 watt, this is slightly more than 1 watt, this is slightly more than maybe 1 point something or 2 watt, So anything above 30 dBm is more than 1 watt, okay, you can see this is 1 watt, and anything around 20-22 dBm is around few hundred milliwatt of power, okay. So these are the kind of powers you are getting at this kind of signal frequencies. This is before the advent of 4G 5G. 1.9 gigahertz, 0.9 gigahertz is actually pre 4G 5G in a way, or maybe 4G 1.9 gigahertz, okay, but 5G is using a slightly higher frequency. In India 5G would be around 3.78 gigahertz, around that, it could be sub 6 gigahertz I would say, not 3.78 gigahertz is one of the band, N78 band, but sub 6 gigahertz. In some countries like maybe North America or so, they could use 28 to 26 millimeter wave frequencies for 5G, but in India we will use sub 6 gigahertz. So this is before the this is a pre generation, 1 or 2 generations before, but you can see that main concept remains the same. What is the device width? Device width is 5 micron, 10 micron, 12, 30 micron. So this is a device width, small width, right, because you need small power, you do not need multiple tens of watts of power, and you can see that power efficiency is to be really high, 65%, 75%, 84.8%. These are really high efficiency numbers. You need that kind of efficiency to actually enable the battery lifetime to be long, okay, and that is something silicon devices find very hard to do. That is why compound semiconductor devices are usually in the handset as a power amplifier, and it just tells you what power amplifiers are this. This is an aluminum gallium indium phosphide in gas pseudomorphic HEMT, I will come to that. This is another pseudomorphic HEMT. Enhancement mode HEMT, which means the threshold voltage is positive. Actually enhancement mode HEMT is very important for a cell phone, because in the cell phone you have a battery, so which means you have a single polarity of supply, which is positive voltage. The battery cannot supply you negative voltage. If you have to have negative voltage, the battery power has to be converted to the negative voltage, which is an additional complexity at the circuit level. So single polarity voltage is there available in the cell phone, so your device better be enhancement mode. So enhancement mode devices, you can see this is enhancement mode, okay. Most of these enhancement mode, these are all pseudomorphic HEMTs. In fact there is a MESFET also, you can see, okay. MESFET also gives you, but it gives you slightly lower maybe efficiency, but depends on the specification of course, but MESFET, this is again for power, here you are talking about power, you are not talking about low noise. These are all for power amplifier inside the cell phone. Low noise amplifier could be most likely a silicon based device, a CMOS or an RF SOI, okay, a low noise amplifier, but power amplifier is usually a compound semiconductor device. And ACPL is something I have not talked about here. It's there are different companies that use different terms. Some companies use ACPR, okay, so adjacent channel power ratio, okay, or adjacent channel power leakage or something like that. So what it means is it's a figure of merit for linearity, okay, because it is here I will just tell you it's a figure of merit for linearity. So what happens is that you have a frequency, suppose you have a frequency at some gigahertz, say 2 gigahertz, you are transmitting the signal at this, but you might also unintentionally transmit signal at nearby frequencies, okay, at nearby frequencies you will transmit signal, and that is unwanted. So compared to this center frequency, that is why this number C comes, dBc, with respect to the center frequency, how much power are you leaking into the adjacent channels, the first adjacent channel, okay, that is your ACPR. It should be as low as possible. So how much power you are getting in the primary channel as opposed to how much you are leaking into the adjacent channels, that is your adjacent channel power ratio or adjacent channel leakage ratio, power leakage, etc., etc. Different companies use different terms, but in a sense this is the main funda. So that is a linearity figure, because if you leak power in the adjacent channels or the other frequencies, then you are basically compromising on the linearity of the system, okay. So this is an important thing, but we will not discuss it right now, okay. This is so essentially for mobile phone, if you want to put your device in the handset, then you need to have higher efficiency, I keep telling you, power density, gain, everything, single linearity and single polarity power, I told you. E mode transistors are very desirable, Pseudomorphic HEMTs significantly outperform MESFETs because of better GM, better channel control, lower gate leakage, etc., etc. You have higher mobility, higher velocity, etc. Okay, great. So this is all about pseudomorphic HEMT. Now, actually people found out that if you have an indium, so in pseudomorphic HEMT, indium gallium arsenide, the indium mole fraction is somewhere between 15 to 25%, no more, because then beyond that this layer will have so much of strain that it will relax and lead to dislocation. If when a layer relaxes, when I say relax, see this InGas has a larger lattice constant like that, it is forced to grow on a smaller lattice constant gallium arsenide substrate, it is forced to grow, and so it is squeezed up. Now the moment, and that is strained, the moment you grow thicker or the moment you grow higher composition, say I want to grow 50% indium gallium arsenide, the strain will be so much, because higher the indium, more is the lattice mismatch, delta mismatch is more between 50% indium in gas compared to say 10% indium in gas, because lower indium means it is more like gallium arsenide, right, and more indium means it is more like indium arsenide. So 50% in gas will have so much of lattice mismatch with gallium arsenide that it will relax. What it means by relaxing is that it will no longer be able to accommodate the strain in itself. So the atoms of indium gallium arsenide will try to go back to their original position instead of being forced to mimic the lattice spacing below. When it relaxes, when a material relaxes on top of another material epitaxially, then misfit dislocations appear, which means there will be missing line of atoms, because if this is your in gas, correct, and this is your gas, for instance, see in the same span you have so many gas gallium arsenide spacings, but only 2 or 1 indium gallium arsenide spacing, and you are forcing them otherwise, but once it relaxes you will have missing line of atoms because of this, okay, and those are dislocations that are not good for devices. That is why you do not want to relax the indium gallium arsenide channel, which means there is a fundamental limit to the composition of indium in gas that you can grow strained on gallium arsenide or pseudomorphic on gallium arsenide, and that is 15 to 20%, but people realize that if you can go to higher indium 50%, 60%, 70% indium in gas, then your mobility will improve significantly, your velocity will improve significantly, your 2dg density also can be improved significantly, because your delta offset, the conduction band discontinuity will be very high, you can confine them better, which means your GM also will improve, your 2dg density will also improve. An improvement in mobility, velocity, 2d electron gas density and transconductance will result in much higher current, much higher cutoff frequency and hence much lower noise figure and much better high speed performance. So, if there is a way to increase the indium content in gas channel, we are going to benefit tremendously for low noise application and for high speed digital application. Not so much for power amplifier. Why? Because for power amplifier you need good breakdown voltage. Indium gallium arsenide, as you keep increasing the indium content, the breakdown keeps reducing, because indium arsenide is a lower band gap material. So, the more indium you put, the lower is the band gap you have. So, 70% indium content in gas will have a lower band gap than say 30% indium containing in gas, and that means the breakdown of 70% in gas will be lower than the breakdown of a 30% in gas. So, if your breakdown is lower, your biasing voltage will be lower, your output power will be lower. So, that is why these are not that attractive for power amplifier, although people have done tricks to overcome that, but these are extremely promising for low noise and high speed digital application, where such kind of HEMTs can significantly outperform pseudomorphic HEMT. Wait, then the question is, how do you enable an in-gas channel with such high concentration of indium gallium arsenide? The key is to use a different substrate, not gallium arsenide, but a different substrate where the lattice mismatch is not high, and that substrate is called indium phosphide. So, welcome to indium phosphide HEMT. When I say indium phosphide HEMT, the substrate is indium phosphide. So, indium phosphide has a larger lattice constant than gallium arsenide, which means you can grow indium gallium arsenide on indium phosphide such that the indium content in in-gas channel can be significantly large. So, people have found that the lattice constant of this is perfectly matched to the lattice constant of indium phosphide substrate, which means it is no longer pseudomorphic, it is perfectly lattice matched. indium aluminum arsenide with 52% indium and 48% aluminum, and indium gallium arsenide with 53% indium and 47% gallium. This material has a 100% lattice matching with indium phosphide substrate. So, indium aluminum arsenide is a higher band gap material, indium gallium arsenide is a much lower band gap material. So, the combination of high and lower band gap gives you a large delta EC. This delta EC is large, which means you have more subband or you can have more electrons in the quantum well. This indium aluminum arsenide in gas HEMTs are called indium phosphide HEMTs. They are not pseudomorphic, they are lattice matched. They are excellent for low noise because of the reasons that I discussed in the previous slide, and also power, also not as good as power as maybe conventional pseudomorphic, but they are catching up. They have tricks to actually overcome that. The mobility of in-gas channel can be more than 10,000 if you increase the indium content. Velocity can be 2.6 into 10^7, which is insanely high. The delta EC is 0.5 eV. This is 0.5 eV, which is much larger than L gas, okay, much larger. So, the sheet density, the 2dg density you can get is 2 times that you can get in a normal pseudomorphic HEMT. Isn't that amazing? The breakdown voltage is lower, as I told you. The in-gas channel fundamentally has a earlier onset of avalanche breakdown, but people have techniques to kind of adjust that or mitigate that to a large extent. Okay. So, this is indium phosphide HEMT, lattice matched, the channel is lattice matched, no strain is there. So, for example, if I look at this image, this is your gallium arsenide HEMT, which you discussed, we are not going to talk about. This is your indium phosphide HEMT. So, the substrate is your indium phosphide, which is semi insulating, you can say. First, people grow indium aluminum arsenide with this composition, which is the barrier from the back side. Then this is the channel, which is your in-gas, 53% indium, 47% gallium is perfectly lattice matched to the substrates or the epi layers below, no problem, no strain. Then the top barrier is 43% again aluminum, 52% indium. This could be uniformly doped or this could have a delta dope. And then you have a cap. The cap need not be gallium arsenide, the cap could be indium gallium arsenide, which is even a much lower band gap material than gallium arsenide. If you have a lower band gap material on top, then the ohmic contact resistance becomes even lower, which is good, okay, which is good. So, having indium gallium arsenide on the top is actually beneficial for the overall system performance in terms of contact resistance also. The reason they put slight p doping is because you want to lift the band from the back side, so that you confine the electrons better and you prevent the back substrate injection. You know, you have a Fermi level here, you have something like that, but you want to elevate that, this part should be elevated, so that substrate injection does not happen. When essentially what I mean is that when between the source and the drain, and this is gate, when the gate is pinch off, the source and drain, this backside connectivity should be as minimum, and that is why this is mildly p type dope to raise the bands up to make the buffer layers more insulating, very mildly by the way. Okay. So, this is your delta EC is 0.51, I told you. In a pseudomorphic HEMT it could be 0.22, much lower. You can get 3 into 10 to the power 12 as opposed to 1 into 10 to the power 12. Mobility could be 10,000, here mobility could be 7,000 in pseudomorphic. Velocity is 2 into 10 to the power 7, velocity is 2.7 into 10 to the power 7. The product of mobility and charge is 3 into 10 to the power 16, this is only 0.7 into 10 to the power 16. So, your improvement in current density in your GM, your cutoff frequency is eminent, is you know, it's imminent, you can see that it is happening. So, if you compare, this is the baseline L gas, okay. This is your pseudomorphic HEMT that we discussed until now, and this is your indium phosphide HEMT. Different parameters are listed. So, in a normal L gas HEMT 0.22 EV is the delta, in a pseudomorphic HEMT it can be up to 0.4, in indium phosphide it can be 0.5, better, higher the better. You can see the maximum donor is 5 into 10 to the power 18, you can give delta doping, you can calculate 5 into 18, here you can give 1 into 10 to the power 19 because the band gaps are higher. The charge density can be 3 into 10 to the power 12, which is really higher than 2 times higher than pseudomorphic HEMT, 3 times higher than normal HEMT. Mobility is much better, velocity is much better, Schottky barrier is also slightly lower though, so the gate leakage could be, you know, low higher, but people can, you know, find out ways to kind of live with that or mitigate that. So, this is the summary of the 3 types of HEMT that we are talking about here. Okay. So, we will end the lecture here because we have to again cover, and there is one more lecture remaining 28, where we are going to discuss about some of the aspects of indium phosphide HEMT that we are talking about here, and we will also introduce the concept of metamorphic HEMT, and then we will conclude lecture 28 this week, where we talked about 3-5 compound semiconductor devices. we'll move on to gallium nitride from next week. Okay. Thank you for your time. I'll see you in next lecture.